Don't you know that the way you learn new things matters the most? The internet is full of scattered information. There might even be books and courses on the topic you are interested in. But by picking the wrong book or ineffective course, you are at risk of wasting your time, money, and most importantly, falling behind your potential competitors. This course was created by experts from the Scandinavian Institute of Business Analytics, experts who know what matters and how to teach. With this course, you will learn exactly what matters for developing skills in SQL for data analysis. You will learn how to use top-notch technologies available in Microsoft SQL Server, the math behind the statistical functions, the way to write your custom functions effectively, transform the data, and connect it with analytics software. Upon completion, you will gain the core data scientist skill. Your ScanBus certificate will prove it to others.
SQL Overview. Relational databases. Relational databases are the workhorses of business data management. They are used to collect, store, and manage transaction data like sales transactions, as well as analyze large volumes of data like those found in data warehouses. It is safe to say the bulk of data used in businesses and other organizations is stored in relational databases. This makes relational databases an important source for data scientists. Now, relational databases are more than just a storehouse for data. They are data management systems that can be used to perform common transformation and analysis operations. Relational databases link data across data stores, filter and reformat data depending on how it needs to be used, aggregate data to provide kind of a big picture summary, as well as answer specific questions about business operations. Let's consider what goes into a production data science environment. To start, we have data sources that can include relational and non-relational databases, often called NoSQL databases. We will refer to both as data stores. Applications and web logs are another source of data for analysis. These are typically less structured than relational data, and they may require significant filtering, formatting, and data extraction operations. Also, small, manually curated data sets that may be maintained in a spreadsheet are often used as a data source. As one can see, data scientists might need data from multiple sources. In these cases, a common practice is to collect data into a single repository prior to analysis. The process for extracting, transforming, and loading data into a data warehouse is called ETL. As the first step of the ETL process, an analyst extracts data from a transaction processing database, an application log, and a personally managed spreadsheet, and then stores all of that in a relational database. If it's a really large amount of data, the data scientist may use a big data platform such as Hadoop. The second ETL step, transformation, is a sequence of operations performed on data to make the data more suitable for analysis. Data scientists often need to reformat dates, replace missing values with zeros, and strip out trailing blanks from strings. Some analyses, like building machine learning models, can require additional transformations, such as changing the scale of numeric values or using even more involved calculations to estimate missing values. Finally, loading is an ETL process step that occurs when data is moved into a data store for analysis. This may sound simple, but large data sets can require specialized techniques, like parallel data loads, to ensure that the data is loaded in a reasonable period of time. Analysis and modeling tools are used by data scientists for a range of activities, like identifying useful information, building predictive models, detecting anomalies, and to make any recommendations. These tools read data from data stores and may write results back to databases as well. Relational databases play key roles throughout the data science process, which ultimately leads to valuable insights into business problems. Data manipulation with SQL. SQL has two types of commands, data manipulation commands and data definition commands. Before discussing specific demands, let's understand why data scientists need to know these commands to do their work. Most data science work is about collecting, cleaning, and restructuring data. Only after that preparation can a data scientist move ahead with analysis work. A common assumption is that about 80% of the time on a data science project is spent on data manipulation. Much of that time is spent working with SQL. SQL has three basic commands for data manipulation: insert, update, and delete. Insert is an SQL command for putting data into a table. Insert statements include the name of the table, the name of the columns with values being inserted, and a list of values to insert. A simple insert command puts one row into a table. The update command is used to change data that is already in a table. The update command includes the name of the table to update, the columns that will be updated, and the new values that will be assigned and, optionally, a where clause that filters which rows will be updated. For example, this command sets the stock price from to 100 for a record with the ticker equal to XXX. If a where clause is not specified, then all rows in a table are updated. The delete command is used to remove rows from a table. The command includes a table name and an optional where clause to determine which rows should be deleted from the table. For example, this delete command removes those rows from the table that have the ticker equal to XXX. If no where clause is specified, all rows in the table are deleted. The select command is used to retrieve data from a relational database. It has many options and features that make it a valuable tool for data scientists who are exploring, collecting, and analyzing data. Here we will only briefly discuss the select command, but we will go into more options moving forward. A select command includes at least one table name indicating which table to retrieve columns from, a list of columns to retrieve from a table, and this may be the special symbol star, which means return all columns. This command shows how to retrieve all columns from all rows in the financials table. Optionally, a where clause can be used to filter the rows returned. As in this example, which returns only rows with the stock price greater than 100. The select command can include more than one table name, a list of columns to retrieve, one or more joins of tables, aggregate functions, and sorting and grouping commands. Data definition with SQL. Part 1. Data definition commands are used to define structures for organizing data in a relational database. Imagine you need to manage thousands of paper reports for your job. Now, you could just leave this in a pile and search through the pile every time you need to find a report. However, it's much easier to find a paper report when they're organized by type of report and then organized within a shelf by name. The same idea applies to organizing data in a relational database. We structure data using tables, which are collections of related data records, indexes, which are sets of data about the location of records, views, which are used when we repeatedly want to access the same set of data from one or more tables, and then finally schemas, which are collections of tables, indexes, views, and other data structures. Tables are used to organize related sets of data, such as financials, events, and information about employees and products. We use the create table command to define a table. The create table command includes the name of a table. In this case, the name is Financials Extended. Next is a list of column names, such as ticker, followed by a data type. Tables typically have multiple columns. Each column is used to store one piece of data, and each column has a data type. Some of the most commonly used data types are integers and varchars, which are for varying length character strings, decimals, and dates. There are many more types for representing more specialized kinds of data, from monetary units to JSON structures. The create table command can have a clause called primary key. This indicates which column or set of columns uniquely identifies each row. When a primary key is defined on a table, whenever a row is inserted into the table, it must have values in the primary key column or columns. Also, that key can't already exist in the table. It has to be unique. However, data scientists often deal with data sets where none of the columns fit the primary key constraint requirements. This limitation can be bypassed. The primary key can be set after the table is created. With alter table command, the data scientist can create a new column ID and set it as the primary key. Then the new column can be filled with integers. In SQL Server, the identity command fills the new column with integers starting from 1 with an increment of 1, for example. This method for adding primary keys is especially useful when data is loaded from a flat file. With SQL Server, a data scientist can load the data into the table using bulk insert command. The command takes the destination table name and the path to the flat file with the data. The data scientist can specify the first row with the data. With that file rows before the specified row will be skipped by the loader. This option is useful if the file has headers. The data scientist can indicate the field and row delimiters existing in the flat file. Another useful option is tab lock. Tab lock locks the tables from other operations while the data is loading. Data definition with SQL Part 2. Often, we want to look up one piece of information in a table. This is like finding a single book in a library. Before libraries had databases, they used card catalogs. These were file cabinets filled with cards with information on where to find books. So you could look up a book by name, and that corresponding card would indicate where in the library you could find the book. Using the catalog is a lot faster than walking through the library, checking every book on the shelves. Indexes in relational databases serve the same purpose. The create index command lets us build an index to quickly look up rows and tables. The create index command takes the name of the index. It's a common practice to use a prefix like IDX to indicate that this is an index. The on clause indicates which table will have the index and the columns that will be used in the index. In this example, the ticker of the company is used in the index. This command will allow the query engine of the database to quickly find the row of data by the ticker. Views are structures that help us focus on the most important data or limit user access to part of the table. Views make it easy to query data without including unneeded columns in our results. Views also help retrieve data from multiple tables without having to repeatedly specify joins. The create view command creates a view. The command includes a name for the view. This view name is View Financials Extended, indicating that it has columns from the Financials Extended table. The next section of the create view command is a select statement, which defines the columns to include in a view. In this view, columns have new names other than those in the original table. This may simplify further work with the view. The from clause indicates the tables used in the view. In this case, it also includes an alias. One more SQL notion we will talk about here is schema. Schema is like a big picture of your data, or you can think of it as a container of tables and views from the same or different databases. Most likely, in your everyday work, you will not be using schemas. However, schema is an important SQL concept, and it's worth being aware of it. The create schema command tells the database management system to create an organizational space, and in that space, we will keep related tables, indexes, views, and other structures. The schema command takes the name of the schema. Here, the name of the schema is myData. If you want to transfer an existing table or view to the new schema, use the alter schema command. You may often meet go command in the SQL statements. Go signals to the server the end of a query batch. Use of go is not required. However, overall, it will improve readability of your code and performance. For example, if you have several query statements enclosed with the go command, and one of the statements will fail upon execution, then the changes made with all the other SQL commands in the query batch will be canceled. Also, you may meet semicolons at the end of the query statements. Placing semicolons is a good practice. However, again, it is rarely required in Microsoft SQL Server. After a table or a view is transferred to the schema, use the schema name as a prefix to the instance name. SQL variants. SQL is a language that has changed over time. Databases offer different versions of SQL, so when we talk about SQL in general, we usually refer to the ANSI Standard SQL. The American National Standards Institute, known as ANSI, defined a standard version of SQL in the mid-80s of the last century. Since then, the standard has been updated 7 times to add features, many of which are useful to data scientists. The foundational SQL commands like insert, delete, and most create commands will be the same across most implementations, but you should check your database documentation, especially for missing data types and functions. In this course, we will be using Transact SQL, a Microsoft dialect of SQL. SQL Server Installation. In this course, we will be using Microsoft SQL Server. Microsoft offers free versions of its SQL servers, which are available to download from the Microsoft website. Search the web for SQL Server Download and go to the download page. For the date the course was created, 2 editions of the most recent SQL Server are available for free download: Developer Edition and Express Edition. We will be using Developer Edition. However, the materials of the course are valid for any version of the SQL Server, including earlier editions like SQL Express 2014. We will also need SQL Server Management Studio to create and execute SQL queries. To operate correctly, the version of the SQL Studio should be the same or newer than the version of the SQL Server. We will be using version 17 with SQL Server 2017. If you are using Windows 7, then you will need an older version of SQL Server. We recommend SQL Server 2014 Express Edition. It also can be downloaded for free from the Microsoft website. The SQL Server 2014 Express release includes the full version of SQL Server 2014 Management Studio. It is okay to use it for our course example file. SQL Express 2014 comes in 32 and 64-bit versions. 32-bit version will suit the needs of this course. After you download and run the installer of the SQL Server 2017 Developer Edition, select Custom Installation and specify the folder for the installation files. Click Install and wait while all the installation files are downloaded to your computer. After the download process is complete, you will see the window of the Microsoft SQL Server Installation Center. Select Installation menu, and then New SQL Server Standalone Installation. Choose the free Developer Edition and click Next. Accept the license terms and click Next. At the next step, after the Management Center prepares the files, select instances of the SQL Server that you want to install. For our course, Sol Database Engine is enough. If you want to practice machine learning using the SQL Server, you will need to add machine learning services to the installation. Then you need to specify a name for your server. In our case, it is LB Lenovo. In the next window, change the SQL Server Agent startup type to Automatic and click Next. Running Server Agent reduces risk of having stale data in your database if you are connected to a dynamic data source. Next, select Windows Authentication Mode. With that, the SQL Server will recognize you through your Windows login credentials. If you want a separate password for the SQL Server, select Mixed Mode and specify your new password. We recommend the use of Windows Authentication Mode for this course. Then click Add Current User and the Server Administrator and click Next. At the Ready to Install step, click Install. That will complete the SQL Server installation process. Now, browse to the installation file of the SQL Server Management Studio and run it. In the opened window, click Install. At normal, the installation process will complete without inputs from the user. After it is done, click Close. Now, navigate to Microsoft SQL Management Tools 2017 and run Microsoft SQL Management Studio. After the SQL Management Studio is loaded, it will prompt you to enter the SQL Server instance name you specified during the installation process. Enter it and click Connect. If you configured SQL Server with a separate password, you will need to change Windows Authentication to SQL Server Authentication and enter your password. Once you are connected to the SQL Server, you can open one of the example files that goes with this course and start your practice activities. To run a piece of the SQL code, select it and click Execute or press the F5 key. To run the whole script, just click Execute or press F5 without selecting the code. SQL Server Data Types. A data type is an attribute that specifies if the object is an integer, a character, a binary string, date and time data, and so on. Most likely, you, as a data scientist, will use only a few of them. Moreover, some of the data types are redundant and kept only for the backward version compatibility. We will cover the most used data types: integer, decimal, real, varchar, var-binary, date, and time. SQL Server uses Transact SQL, or T-SQL, a Microsoft dialect of the structured query language. The data types that we will describe in this course are common for Transact SQL. One of the reasons for various data types is the optimization of space under the database. Queries executed on the space-optimized database run faster. Also, SQL servers with optimized databases require less expensive hardware to operate. Int data type reserves 4 bytes for storing integers in the range between around -2 billions to +2 billions. Integer data types are often used for creating primary keys in the tables, for example 1, 2, 3, etc. For example, in this create table command, the primary key is integer variable ID. In Transact SQL, decimal is synonym to numeric data type. Arguments of the decimal data type are the fixed precision and scale numbers. For example, stock price decimal 6,2 means that numbers in the variable stock price can hold no more than 6 digits in precision and 2 digits in scale. Scale must be less than precision. If you are not sure of how much scale and precision places you need, it is okay to skip these parameters and use only word decimal alone. With that, SQL Server will reserve 17 bytes, enough to store a 38-digit number, which is a lot. Real is an approximate number data type used to store numbers with floating points. An SQL Server uses 4 bytes to store real numbers. Real numbers range from very small fractions to very large numbers on positive and negative scales and include 0. Real numbers use a little less space than decimals. However, if the database performance is not an issue, use decimal instead of real. Varchar stands for Variable Length Non-Unicode String Data. If your data is Unicode, use N-varchar data type. If you have values from different languages in the same column, then use N-varchar. Varchar data type is more constrained. This is a preferred way for storing words in plain English or commonly used natural keys like a license plate, serial, or phone number. Loading Unicode data into varchar variables may result in the appearance of extra question marks in the variable values. The number in the varchar data type bracket defines the string length and can be a value from 1 through 8,000. Here, varchar 5 means that the SQL server reserved a place for 5 characters for the ticket variable. If you do not know the maximum length of the string in your table column, use the word max instead of the number in the varchar brackets. Max indicates that the maximum storage size for each variable is about 2 gigabytes. Var binary data type is for storing variable length binary data like PDF files or images. Var binary is similar to varchar, except that varchar is a Unicode-based type data store, while var binary stores the perfect copy of your data without any conversions. Var binary with max in the bracket indicates that the variable can hold up to 2 gigabytes. Date data type supports a variety of date formats. Basically, any date format you can meet in Microsoft Office applications like Excel, you can find in SQL Server. With SQL commands year, month, and date, you can get year, month, and date as integers from the date variable. You can also use these commands in filters when retrieving data from the table. Time data type defines a time of a day. The time is based on a 24-hour clock. Please mind that time variables do not store time zone information and use time of the SQL Server machine. The number in the brackets next to time specifies the number of digits for the fractional part of the seconds. The default is number 7, which is equal to the precision of 100 nanoseconds. Same as date, time data type supports various time formats. Again, you may find the same formats in the Microsoft Office applications, for example. To get hours, minutes, or seconds from the time variable, you will have to convert it to the string variable and use string manipulation commands. Statistics with SQL. Create table and load data. After we connect to SQL Server, we see a list of objects in the right window of the SQL Server Management Studio. As we will create new objects, we will populate this list. At first, we need to create a new database. For that, we will open a new window for SQL queries. We can click on the New Query button by hitting Control key +N. In the new window, we will type in an SQL command for creating databases with the new database name. Create table SNP 500. Enclose the statement with Go to create a query package. Go statement is not a must if you are using an SQL server. However, in larger SQL codes, the use of a Go statement improves server performance, allows undos, and eases code readability. So, it is a good practice to use Go in your SQL code. To execute the SQL command, we select the SQL code snippet and click Execute. To refresh the list of databases, we right-click on the word Database and select Refresh. After refresh, the new SNP database shows up in the database list. When we connected to the SQL server, the default database was Master. This is a system database which exists on every SQL server. Since we are going to execute SQL queries on our new database, we need to switch the active database to our SNP 500. In SQL Server Management Studio, we can do that with the drop-down menu. The same action can be accomplished with the SQL statement Use SNP 500. Note that after we execute this statement, the active database name in the menu changed from Master to SNP 500. Next, we will create a new table, Company by Sector. At first, we will create the table structure with the Create Table command. Here we must specify new column names and column data types. The numbers in the data type brackets show maximum length allocated for the values in the column. For example, varchar 5 for ticker means that ticker string could not be longer than 5 characters. Varchar 50 for the company name means that the company name string cannot be longer than 50 characters. If you do not know what length to expect, just type the word max in the brackets. Execute the create table command. Expand the S&P 500 database object. Expand the list of tables. Expand the company by sector table object. Expand the list of columns and ensure the columns were created as described in the create table command. Now it's time to populate the table with the data. For that, we will use SQL command bulk insert. We will load the data from the text file with commas separating values. In the bulk command, we have to specify the path to the file with the data, the row number where the data starts. In our case, the first row in the file is reserved for column headers. Also, we need to specify the column field and row delimiters. Tab lock statement restricts the access to the table while the data is loading. In our CSV file, the first row has the column headers. The number of columns and the data types in the created table should match the number of columns, their order, and data types in the file. Otherwise, the SQL server will generate an error and will not load data into the table. After the command is executed and the data is successfully loaded, the SQL server reports how many rows were loaded. In our case, all 505 rows were successfully loaded. To check the data, we can right-click on the table name. And then click Select Top 1000 Rows in the drop menu. The SQL server will automatically create a Select SQL query in the new query window and execute it. As a result, we will see the content of the table in the message window. Alternatively, we could write the same select query by hands and execute it with the Execute button or F5 key. The Company by Name table includes columns for the ticker, company name, sector, stock price, and is populated with data from our CSV file. We will be using this table to demonstrate how to use SQL for data analysis. Count, min, max, top, and distinct. After we connect to our SQL server with the SQL Server Management Studio, we see the list of objects in the Object Explorer window to the left. If we expand the cascade of menus under the database object, we will find the previously created table. Clicking the New Query button will open the new window for SQL commands. One thing to pay attention to here is that the default database is master. We need to select our database from the drop-down menu. Alternatively, we could run the use command. The first command we will execute is the select query with asterisk that lists all values from all columns in the table. The results of the query execution are shown in the new window below. Often, for the data overview, we need only the first several rows instead of retrieving all of them. This is especially useful when working with large tables. The top command will restrict the select statement to the first 10 rows. After we execute the select statement with the top command, the result window will show the first 10 rows of the table. Now we will show some basic aggregate functions. The first function is count. The following count command counts the number of rows in the table, which is the number of companies. If we want to count the number of companies in each business sector, then we can use the group by clause. Here we indicate that we want to count all companies in each sector with the group by sector statement. We can assign a name to the second column with the counts. Here we will call it as number. The results window shows a table with two columns, sector name and the number of companies in this sector that we found in our data. Now, let's look at a couple other aggregate functions that are commonly used. Those are the max and the min functions. Let's say we want to know what the highest stock price in our table is. We will use select statement with the max function. We will name the new column as max stock price. Similar statement structure can be used to find the lowest stock price in the table. For that, we will use min function instead of max and name the new column min stock price. As before, the result window shows the result of the query execution. Sometimes we want to see both the max and the min values at the same time. No problem. For that, we can include both the max and the min in the same select statement and execute it. Notice that the maximum and the minimum both returned in the result window. Just as we can count rows in groups, we can also apply the max and min functions to groups of subsets of rows. With the following select statement, we can find the minimum and maximum stock price for companies in each business segment. Note that we will not only group by segment, but also include the segment name in the results. Another command that you will often meet in select statements is called distinct. For example, if you will select names of the sectors from your table, you will get a number of duplicating records. To reduce the number of records by removing duplicates, you can use the select statement with distinct command. As you can see in the results window, the reported list of sector names does not have duplicates and only has unique names. This simple yet powerful command will help you deal with redundant data in your data scientist's work. Statistical functions in SQL. Data scientists often use statistics to better understand datasets. SQL includes functions for describing datasets. We will cover the most commonly used statistic functions: sum, average, variance and variance estimator, standard deviation, and its estimator. The most commonly used function is sum. The sum of a column returns the algebraic sum of all values in the column. Note here that your values have to be numbers. If your values are stored as characters, you need to convert it to a number format like integer, decimal, real, or other. The next popular function is average. In SQL, average is the algebraic sum of all values in the column divided by the number of rows. Empty rows do not count. Functions for calculating variance are not so obvious and have to be explained. Variance is a good way of measuring how spread out the data is. SQL has two functions for calculating variance, varp and var. The difference is that varp calculates the variance of the data you have, while var estimates the variance of the whole data you could have. Imagine you want to know the variance of the water consumption per household in your city. You have the data for one district only. The function varp will calculate for you the variance of your existing data. Here it is a variance of the water consumption per household in the district. In math language, varp calculates statistical variance for the population. P in the function name stands for population of data you have. If you want to estimate variance of the water consumption per household for the whole city, based on the data for only one district, then use var function. Note that the functions differ only in the denominator. Varp has n in the denominator, while var has n minus 1 and will return greater values than varp by default. Remember that var is an estimator and use it with care. In most of your applications, you will use the varp function for calculating variance of your data. Similar notations are true for standard deviation functions in SQL. Standard deviation is a more commonly used statistic for understanding the distribution of data. Function stdevp returns standard deviation of your data. while stdev function returns an estimator of the standard deviation of the data you could have if you continued to collect it. In some sense, the stdev function is trying to predict the standard deviation of all possible values of the variable. Sometimes you will hear that stdev is biased and stdevp is an unbiased standard deviation estimator. The bottom line, use stdevp function for calculating standard deviations in SQL and report it as the standard deviation of the data we have, unless you really need the standard deviation estimator. Now, let's see how to apply these statistical functions in practice. For that, we connect to our SQL Server with the SQL Server Management Studio and click New Query button. Since the table we will be working with is in the S&P 500 database, we select this database in the database list. At first, we ensure that the table has the data we are going to work with. With the Select * query, we can view the table content in the results window. Next, we calculate the sum of all values in the stock price column with the sum function. In this example, we use the table with the stock prices for the sake of consistency with the previous exercises. We can calculate subsums of the stock price variable by the business sector. For that, we will use Group By clause. Remember to include the sector variable name in the select statement. Now we add the average function to the select statement and calculate average stock price for each business sector and report it in the same output table. Similar select statements with varp and var functions returns variance and its estimator for the stock price variable. Replacing functions for variance with the functions for standard deviation, we calculate standard deviation and its estimator for the stock price. The reported values are grouped by sector in the same manner as previously. Let's calculate the average values again. Note that the reported values for the average stock price has a lot of digits in the scale part. We can round the average stock price values using the round function. Here we round average values to hundredth part. For that, we set the second argument of the round function equal to 2. If we would like to round to thousandth part, then we would set it to 3 and so on. However, we still have the trailing zeros in the average price values. The problem is that in SQL, the average function returns the average value with default decimal places, which can be different for the variable format. To solve this, we use cast function. Cast function can convert SQL variables from one format to another. There is one more function for that, called convert, that does the same conversions as cast, but also can apply styles, which is useful in converting dates. Now, after we applied the cast function, we converted the average values to the same decimal format as we have for the stock price variable. Filtering data. A common task in data science work is filtering data, so we can work with just the data we're interested in. With the where clause, we can filter numerical and character data. Where clause can contain several filters combined with the Boolean logic. Filtering numeric values is straightforward. We'll use the company by sector table for this example. Let's assume we want to list every company with a stock price greater than 1,000. Since we only want to include a certain subset of the companies, we use a where clause. We will set the numeric filter to show the companies where the stock price is greater than 1,000. As a result of the query execution, we receive a subset of data with the list of companies that satisfy our filter settings. Filtering based on character strings works in similar ways. Now let's generate a list of companies which belong to the information technology sector. We create a new filter where the sector column values should be equal to information technology. Now the query execution results window has all companies belonging to the information technology sector. Now we can combine the two filters. Composite filters are quite common. Sometimes, where clauses can be the longest part of a select statement because there are so many conditions that need to be satisfied. To filter for rows that satisfy both conditions, we use the AND keyword. For example, we want to find companies from the information technology sector with a stock price greater than 1,000. For that, we combine the two filters we previously created. The query results show two rows which represent one company, Alphabet, that owns Google. The two tickers are the result of the stock split in 2014. Now, if we want at least one of the conditions to be met, but maybe not both, then we can use the OR keyword. In our filter, we change the AND to OR, execute the statement, and observe that there are two companies in our data set which are not in the information technology sector. Let's stop here and talk about code formatting. You probably noticed that we started using left indent in the query strings. There is no single rule for styling the code. However, we think it is a good practice using indents in complex queries. SQL is a programming language. As with any other language, you may like to take an extra effort to improve readability of your queries. This will pay off later when you will start editing and debugging your code. Now let's move on to the character filters. In SQL, the like operator is used to determine whether a character string matches a specified pattern. A pattern can include regular characters and wildcard characters. There are many options for working with the like operator. Before we show the example, we want to explain what the term wildcard character means. Wildcard character is a special symbol which can stand for a certain range of characters. Here is the table of wildcard characters used with the like operator. The most used wildcard character is the % symbol. It represents any string from an empty space to a string with any number of characters. For example, if we wanted to find all companies with the abbreviation Inc. in the name, then we should construct the following filter. With that, we include companies that have a comma after the Inc. string. Note that we added a space in front of the Inc. to distinguish the abbreviation from Incorporated from an accidental case where the company can have Inc. characters inside the title. If we add not to the like operator, then we can filter companies with the names that do not have Inc. in their names. We need to mention that you have to be careful when using % at the beginning of a string. When this happens, the database cannot use indexes that may be on the column. This will cause the database to scan every row in the table looking for matches. It will still work, but might take longer time than you expect. Another example of using like operator with the % wildcard is to list companies whose names start with A. We can create composite filter and list companies whose names start with A or B. For that, we can use two filters with a % symbol which start with A and B. We can also use the square bracket wildcard to construct the same filter. If we want to list companies with the names that do not start with A or B, we can use not like operator or square brackets with the caret. If for some reason you are looking for companies with 6 letters in the title, you can use the like operator with 6 underscore wildcards. Alternatively, you can use the len function that returns length of the string. Query with the filter where length of the string is set to 6. This will return the same results as the query with the underscores, but is more readable. Subqueries. We usually select data directly from tables and views, but sometimes we might need to get data from the results of another select statement. We can do this using SQL subqueries. Subqueries can be used in 3 different parts of a select statement: in the select values list, in the from clause, and in the where clause. Let's work through an example of each of these 3. At first, we will introduce concept of prefix. Since we have multiple select statements within a single query, we'll want to make sure the database can tell which table each value comes from. To do this, we will use a table alias and include that alias as a prefix for each value we will return. In our example, the table company by sector has alias T1. So all columns retrieved from the table T1 has to have the prefix T1. Now we will create a subquery that will calculate average stock price by sector. For that, we will use the same table, company by sector, but with a different alias. We will call it T2. We add a restriction that we are interested in the average by sector, and the sector names in the table T1 and T2 should match each other. In some sense, we are joining our table T1 with the list of calculated average values. We will look deeper at the join conditions when we study table joins. Let's look at the query one more time. Here we have the subquery that calculates the average stock price from the company by sector table, but only using rows where the sector name is equal to the sector of the company the algorithm is currently looking at. Note that we place the subquery where we would usually have a column name. We call the new column sector average. In the results table, we see that we have added an extra column, sector average. This column lists the average stock price for the corresponding sector. Let's look at another example of how to use subqueries in the from clause. At first, we construct the plain query for retrieving sector names and stock price values from the company by sector table. Now we want to know average stock price by sector, but we are only interested in companies with the stock price greater than 100. We can find this information by constructing a subquery in the from clause with the where filter. Basically, we will select from the results of another select statement. As before, we will add an alias T1 to name the results of the subquery. Here we add one more clause, group by, for explaining the SQL engine that we want to calculate average stock price by sector. The results table shows the list of sector names with the average stock price. Note that only the companies with the stock price greater than 100 were included in the average. You may notice that we did not use prefix in the column names. We did so to demonstrate that the SQL engine is smart enough to understand our needs. Here you may see that the results of the query with prefixes are the same as without. However, we recommend using prefixes for improved readability and debugging purposes. Prefixes are essential when you work with more complex queries. Another place where you can incorporate subqueries is the where clause of the select statement. These subqueries can be used when we want to make comparisons within a single table. For example, if we want to find the sector of a company with the highest stock price, we can use a subquery in the where clause. This subquery will find the maximum stock price in all sectors with the max function. Then we will use this maximum value in the filter to find the company sector name. Note that we used different aliases and prefixes T1 and T2 for each select statement. This query will work without aliases and prefixes. However, we recommend using it. Also, you might note that we used single spaces as the indents. Again, use of single or double space indents or not using indents at all is a matter of style. We intentionally vary indents along the examples to demonstrate various styles. You pick the one that works best for you. Combining Tables, Part 1. You might hear the term joining tables, which is a common operation in SQL. However, the range of commands that SQL Server has for combining tables is wider. We will cover joins, union, intersect, and except. Table joins is one of the key features of the structured query language. When working with data, we sometimes need to retrieve data from two or more tables. For that, SQL has several variations of join command: inner join, left, right, and full outer join, and cross join. Although the join commands work with tables, sometimes for illustration purposes, the tables are shown as circles. The inner join command, or the simple join, returns a table that has records which conform between table A and table B. Here we should say that in order to make the join possible, both tables should have similar columns. For example, table A has stock tickers and the stock prices, while the table B has stock tickers and company names. The joined table will have the list of stock prices and company names for cases where the rows in both tables have the same tickers. We will explain this statement when we show examples. The left outer join results in a table that has all rows of the left table, table A, and rows from table B, the right table, that match the join condition. The right outer join is the inverse of the left outer join. Actually, the words inner and outer are optional when it comes to the writing the commands. It's okay to skip it. You can write and say only join instead of the inner join, and left join or right join instead of left outer join or right outer join. The full outer join command produces a joined table that has all rows of table A and table B. The columns with unmatched rows in the resulting table are empty, or, better to say, are filled with the value of none. The cross-join command can be considered exotic. However, there are cases when it helps to reduce the amount of data manipulation actions. With the cross-join command, we can generate a data set where for each row in the table A, we will have all rows of table B. The following examples will clarify each of these join commands. In this example, we will demonstrate how to use the join commands. At first, we will create two tables in our S&P 500 database. For that, we will use the create table command. The new table, named Table A Company Stock Prices, will have two columns, the column with tickers and the column with the stock prices. We will populate the table using insert command and insert values for tickers and stock prices in 4 rows. The insert command is used to add new rows to the table one by one. To add 4 rows, we need 4 insert statements. Now we will create another table named Table B Company Names with 2 columns, ticker and company name. We will add rows to this table in the same manner as before using 4 insert statements. The first 3 rows will contain the same tickers as in Table A. The last column will contain ticker that does not exist in the Table A. We made that to illustrate the difference in the join commands moving forward. Now let's select data from Table A and Table B and execute the 2 select statements in the same query batch bounded with the Go command. Note that 2 select statements in one query batch resulted in 2 tables in the output window. Also note that the 4th rows in both tables have different company tickers. Now we will give an example of the inner join command. This select statement will combine ticker, company name, and stock price columns from Table A and Table B. The join operation is performed on the column ticker. To differentiate the tables, we add prefixes TA and TB to the column names. The result of the inner join operation is a new table with 3 rows with ticker values, company names, and stock prices of those companies. The 4th rows in each table were skipped since the ticker values did not match each other. The keyword inner in the inner join command is optional. The same query will work in the same way without the inner keyword. Now let's examine the left outer join command. The select statement is similar to the inner join command that we created before, except now the join command is called left outer join. The resulting table has 4 rows. All data from the left table, here Table A, is included. However, the last row has the null value in the company name column. This happened because the right table, Table B, did not have information on the company name for the record with this ticker. It did not have such a ticker at all. To create the right outer join select statement, we need to replace the word left with the word right in the join command and change the prefix in front of the ticker column name. Now we need all data from the right Table B and only rows that match Table B ticker values from the Table A. Look at the resulting table. The last row has the null value in the stock price column. This happened because the left Table A does not have stock price data for this ticker. This is a mirror-like situation to the previous example. Note that if we did not change the prefix in front of the ticker column name and retrieved tickers from the left column A in our right join statement, then we would get the awkward results where the last row either did not have the ticker value or the stock price value. In the same way as the inner join statement works the same without the optional keyword inner, the outer joins work the same without the word outer. These keywords are used to ease reading of the SQL code. Now let's see what happens if we execute the full outer join command on the tables A and B. The full outer join command includes all rows of the table A and all rows of the table B. Since we join tables on the ticker column, we will get the table with all the ticker values. The rows that did not match tickers from both tables will have null values in the cells. Here, the 4th row has the null-valued cell in the company name column. The 5th row has the null in the stock price column. The last join operation we will consider here is the cross join. For that, we will create another table called Group Numbers with one column, Numbers. We will populate this table with 3 integer values using the insert command. With the select statement, we check that the new table is properly populated with the values 1, 2, 3. To construct the cross-join select statement, we will use the select statement we created for the inner join. We will select ticker, company names, and stock prices from the inner join select statement and cross-join it with the group number table with the only column number. As with all join statements, we will create aliases to the table names and add it as prefixes to the column names. The resulting table has the data in 3 sets of repeating rows. The ticker, company name, and stock price values came from the inner join of Table A and Table B. Each row in this inner join is then repeated for each row in the group number table. This is how the cross-join operator works. As a result, we tripled the table we get from the inner join. Sometimes you will need double or triple data sets in your data science work. For that, you can use the cross-join operator, which is quite handy. Combining tables. Part 2. In the previous section, we considered join operations. Joins used with filters can create almost any combination of tables. However, the join statements easily can become too complex to read and expensive for the server to execute. To simplify the code structure and to improve SQL Server performance, sometimes we can use union, intersect, and except commands. In contrast to the join command, these commands work only with rows. In other words, all datasets in these commands should have the same columns. To illustrate these commands, we will depict tables as circles and place the circles one below the other. The commands union, intersect, and except can merge the tables with equal columns, return the common rows, or subtract one table data from another. In the example section, we will show how each of these operators works. We will start with creating 2 tables in our database S&P 500. Both tables will have 2 columns, company name and stock price. We will fill the tables using the insert command and add 3 rows into each. The only difference in the 2 tables will be the last row. The last row in Table A will have a different company record from the last row in Table B. We will use 3 rows for the illustration purposes only. For the commands we will show, the number of rows in the tables can be different. With the 2 select statements, we will check if the tables were filled with the data as expected. The 2 select queries are executed in one batch, so the result window shows 2 outcomes simultaneously. This is convenient when you want to compare 2 data sets. Now we will take these 2 select statements and combine them with the union statement. As a result, we will get a table where all distinct rows from Table A and Table B are united into one data set. If we want to combine all rows from Table A and B, ignoring possible data repetition, then we can use the union all command. Note that the resulting table has the repeating rows. The reason is that part of the data in Table A also exists in Table B. Remember that we intentionally constructed the tables with the repeating data. To list the data that is common in both tables, we can use the intersect command. The select queries with the intersect will only return rows that exist in both Table A and Table B. Lastly, if we want to find rows in the Table A which are unique for this table and do not exist in Table B, we can use the except command. As you can see, these 3 commands, union, intersect, and except, are quite handy to use. Together with the join command, they form a powerful set of operators for combining tables. You will often meet these commands when you are working with views. Creating a view. Often, you will create complex queries that will join and filter data from one or more tables. If you will routinely use the results of such queries, we recommend creating a view. A view is a database instance that looks much like a data table, except that this is not a real table. It is, rather, a result of an SQL query. Before we start working on views, we will demonstrate a feature of the SQL Server called Query Execution Plan. At first, we will create a select query in our S&P 500 database. This query will use average function and list average stock prices in each business sector. The query will include only companies with stock prices greater than 100. Before we execute the query, let's take a look at the execution plan. For that, we should select the query of interest and click the Display Estimated Execution Plan at the menu bar or press the Ctrl+L key. The result window at the bottom will show a scheme. The sequence shows the execution plan for the select query. Below each icon, the SQL Server Management Studio shows estimated time in percent of executing each operation or the cost of the operation. This functionality will be especially useful if you will be working with large data sets and complex queries. Knowing the estimated execution plan, data practitioners can rewrite the query and make it more cost-effective. However, we showed the estimation plan for another reason. Now, let's execute the query, ensure that it generates the result we expected, and create a view from this query. We will use the Create View command and name the view Top Sector Average. To see the list of the views in your database, we can expand the database tree in the Object Explorer window and find the branch named Views. Now let's write a query for retrieving all data from this view and see its estimated execution plan. For that, we select the query and click on the Display Estimated Execution Plan button. Note that the estimated execution plan for this simple query is exactly the same as for the source query we used to create the view. The reason is the nature of views. Views are not real tables, but rather virtual tables. When we created the view, no data were copied or moved. The data still exists in the same table. We only created an alias for the query. Now let's delete this view with the drop view command and create another one. Although the views are virtual tables, the importance of views for some applications like data warehouse is so high that the question of data retrieval performance becomes increasingly important. In this query, we select several columns from the source table and apply the filter. The resulting dataset has unique ticker values in each row. Now, we will create a view from this query and then create an index for this view. Indices can improve the query performance and, as a result, improve performance of views. We will call this view Incorporated, since it will let us view only the companies with the abbreviation Inc. in the name. Since we know that we are going to create an index for this view, we will bind this view to our schema called DBO. For that, we will use the keyword schema binding in the create view command and place the source table name in the square brackets with the database schema as the prefix. Let's select all data from this view to ensure that it is all set. Now we can create the index. We will use the create index command with the keywords unique and clustered. The first index for the view has to be clustered index. We will create the index on the column ticker in the view named Incorporated. The new index will be stored in the database under the same schema as the view. Now, all select operations with the indexed view will perform much faster than the query we used as the source for the view. You will note the performance improvement when you are working with large data sets. To delete the index, we can use the drop index command. Note that we should indicate the name of the view as the prefix for the index name. Finally, we can delete the view using the drop view command. Deleting the view is not the same as deleting the table. After the view is deleted, all our data will remain safe and untouched. Grouping and ordering. Grouping and ordering data sets is very easy with SQL. Let's see how this can be done on the examples. With the clause order by stock price, we can order the results by the stock price in ascending order. If we want to be explicit, which is always recommended, we can add a keyword ASC to indicate the sorting goes in ascending order. We can order the records by the stock price in descending order by using the keyword DESC in the order by clause. SQL can also sort by string variables. For example, we can sort our data set by the company name. With the keyword DESC, the sorting will be in reverse alphabetical order. The first rows in the resulting data set will have company names which start with the letter Z. Use of an ASC keyword will sort the results in regular alphabetical order from A to Z. In SQL, grouping is also straightforward. In this query, we will calculate average stock price by sector. For that, we will use the group by clause with the sector variable. One thing we should mention here is that the select statement should only have the variable that you are using in the group by clause. In other words, if you will try to select sector variable and the company name from the table, the query will generate an error since the company name variable is not in the group by clause. Lastly, we will show how to perform filtering on the grouping results. For that, we will use the having clause. The having clause is like the where clause we use in filters, except the having clause can filter the results of grouping. Here, the query will return the list of business sectors and the average company stock prices in each sector sorted in ascending order. Note that because of the having filter, the resulting set includes only stock prices greater than 100. Partitioning. One of the greatest things that SQL can do with the data is automatically creating subsets of data and performing calculations on it. The function that can create subsets or partitions of data is called partitioning. The command that tells SQL to perform calculations over the subsets is called the keyword over. Combined, the function is called over partitioning. We will demonstrate how to calculate average on the subset of data. Count the number of records in the subset, calculate rank of the record, show the row number, and split the data into a fixed number of subsets or tiles. Before we start, we will recall how we calculated average in our previous examples. For that, we used the average function with the group by clause. The limitation for this query structure is restriction on the list of columns in the select query. We cannot list other table columns in the query like this. The overPartition function removed this limitation. We can construct a query with the list of the table columns, calculate average stock price in each sector, and display it as the calculated column. This query tells the SQL server that we want to calculate average stock price on the data set partitioned by the sector variable. The records with the same value as the sector variable will form a separate data subset or partition. Now we will count how many companies are in each sector. For that, we will use the count function with the over partition clause. Note that we use the keyword distinct to avoid repetition. Since SQL attempts to show the count values for each company name in the table, we do not need this. We also want to sort the results by the number of companies in each sector in descending order. For that, we use the order by clause with DESC abbreviation. Next, we will calculate rank of each company in each sector by its stock price. The SQL function rank will serve our needs. The following query tells SQL Server to partition the data set by the sector variable values, sort the companies in each sector by the value of the stock price, and assign a corresponding rank to each record. The company with the lowest stock price in the sector will have the rank of 1. The following company with slightly higher stock price will have the rank of 2, and so on. The highest rank will have the company with the highest stock price in the sector. If the two companies have the same stock price, then they will have equal ranks. In a similar table, we can generate replacing the rank function with the row number function. In this query, the companies are sorted by the stock price values in each partition. The row number function returns the place of the record in the partition. The difference with the rank function is that if the two companies have the same stock price values, then its row numbers will be different, while the rank functions will return equal values. SQL has a function called entile. This function can split the data set into a fixed number of subsets. The number of subsets is the integer argument of the entile function. Sometimes you may need to split your data into several bins or tiles. For that, you can use the entile function with the partition clause. In this example, we will split companies in each sector into 4 subsets or 4 tiles. As you can see, the 4 subsets has seemingly equal number of records with each sector. However, this is not exactly so. The entile function does not always split the records into the equally sized tiles. They are about the same, but not strictly equal. Unfortunately, we cannot control the exact number of records in each tile with the entile function. That is why we recommend checking the size of each subset before using the results. To see the actual size of each file, we can create one more query on top of the query with the entile. In this complex query, we will select data from the partitioned dataset and count the number of companies in each tile. As we can see from the query results, the entile function split the dataset into about equal tiles, but not of the same size. Use the entile function with caution. Date and time, Part 1. We talked about how to work with numeric and character data formats. With SQL, it was relatively simple. However, when it comes to data and time, there is no single recipe. The challenge is in variety of possible data formats. In your work, you may meet date records in various styles and languages. We will show you how to import the date and time records into the SQL tables and deal with the variety of styles. SQL has 2 main data types to work with date and time. These data formats are called date and time. Very natural. But we recommend importing your date and time records as strings. After that, you can attempt to recognize the correct date and time format and convert the strings to date and time data types. For the data type conversion, the SQL Server has several functions. The cast function is the most common SQL function. With cast, you can convert between all major SQL data types: numeric, character, and dates. The convert function is similar to cast. The only major difference is that with convert, you can specify the style of the date format when converting from strings to dates. Most likely, you will never need the style option in your data science work. Parse is the most advanced function for converting strings to dates. It can understand most date formats. Be aware that parse is not a native SQL function. You have to have a .NET framework installed on your machine to make the parse function work. Parse is a function of the Microsoft .NET platform that you can seamlessly run on your SQL server. If your servers are remote, then quite possibly the parse function will not work. So use parse with caution if your SQL scripts will work in a production environment. The three more functions, try cast, try convert, and try parse, are the same as cast, convert, and parse, except that it will not throw errors if the conversion will fail. Instead, these try versions of the function will silently return null values and will not stop the SQL execution. To demonstrate how to convert strings to the date format, we will create a table in our S&P 500 database. The table will have only one column in varchar data type. We will populate the column with strings containing dates in various formats. Let's check that the table is populated with the data as expected. Now we construct a select query with three functions, try cast, try convert, and try parse. These functions will attempt to convert our records into the date format. After the query is executed, we can examine the results of conversion of each function. We can see that the try-cast and try-convert functions performed equally successfully and failed on the same records. The try-parse function did the better job. It managed to convert all records to the date format correctly, except the last one. Fortunately, the parse function has an option to change the date regional settings, or culture, in the terms of the .NET framework. In the new select query, we will indicate that the records should be treated as if it came from Finland. For that, we set the try parse to use the Finnish style of date recording. As we see from the resulting table, the try parse function correctly recognized the last record and converted it to the date format. However, now it does not recognize some dates recorded in a format that is not used in Finland. In your data science work, you may need to vary regions and converting functions to enable correct date conversion. To help you with that, we included culture codes for various languages that you can use with the using command in the parse and try parse functions. If you will be using the parse function a lot, you will notice that it is not as fast as other SQL functions. Part of the reason is that parse is not a native SQL function. To improve performance, you can copy your select statement results into a new table. With that, you will have to convert dates only once, and then just retrieve the converted data from the table you created. You can create a new table with the select into command. The command is much like the standard select statement, except that you indicate a name of a new table where you want to copy the results of the query. The SQL server will automatically create the table and copy the results. Selecting from the new table will be much faster. You will notice the performance improvement when you will be working with large data sets. Date and time, Part 2. As you saw, converting date and time is not something that can always be done with a routine procedure. Now we will introduce one more converting function that is native to the date and time formatting called datePart. But we will not stop here. We will move one step ahead and explain how string functions like ltrim, substring, and concat can help when all-over conversion functions fail. To start, we will create a table with a string column and fill it with time records in the string format. As we said before, we recommend you start working with date and time records with the string format and then convert it into date and time. The string records that we insert have 3 sets of numbers, each separated with a colon. It stands for hours, minutes, and dates. We intentionally placed leading and trailing spaces around the digits. In real-life records, we will meet all kinds of formats and obstacles. Now we will convert the string records into time format with the try-parse function. As you see from the resulting table, the parsing function did its job well and converted the strings into the time format. With the datepart function, we can extract information about hours, minutes, and seconds. For that, we will apply the datepart function to the results of conversion and use the appropriate keywords, hour, minute, and second. The result of this query is a table with 3 columns that contain information about hours, minutes, and seconds. There are more keywords that you can use with the datepart function to get even deeper insight into the date and time records. So, we successfully extracted the information on time from our string records. But what if the parse function fails or is not available? We will show you how you can parse the string with the means of the SQL string functions. At first, we will use the ltrim function to cut out the leading spaces in our records. If we would like to cut out trailing spaces, then we use the rtrim function. Since we know that our records have 3 sets of digits divided with a colon, and each set stands for hours, minutes, and seconds, we can extract these 3 parts with the substring function and call it hours, minutes, and seconds in the string format. The substring function takes 3 arguments: the name of the string variable, the starting position of the substring, and the length of the substring. We can see from the resulting table that our string parsing process works. Now let's create the true time variable from the results of our string parsing efforts. At first, we will concatenate the strings with information about hours, minutes, and seconds. But the concatenated string should also have a colon as the separator. That will help to convert it to the time format. So we construct a nested query where we get the inputs to the concat function from the previously created select query. Finally, we need to convert the concatenated string into the time format. We can do that with the convert function. As we can see from the query result, the conversion was a success. Now you know how to convert your date and time records into the date and time format and use it in your data analysis work. Programming with SQL. Mathematical functions. When we think about solving analytical problems, we often think of programming languages. Structured query language was made primarily for retrieving data from databases and operating with tables. However, it can be used for some basic mathematical analysis. Actually, if you think of making calculations on tables, we recommend thinking of SQL first. SQL comes with a handful of built-in mathematical functions. We will cover those that you will most likely use the most and show how to run it on the SQL server. The first two functions we will start with are ABS and sign. The first function returns the absolute value or module for the number, and the second checks for the sign. If the number is positive, the sign function returns 1. If negative, then -1. The rand function returns a random float number between 0 and 1, excluding 0 and 1. This is the only non-deterministic mathematical function in SQL. If you will provide the rand function with a seed as an arbitrary integer value, then the outcome will be reputedly the same throughout your script, no matter how many times you use the rand if the seed is the same. If you do not provide the seed, then the rand function will generate different random float numbers on each function call. The exponent, square root, square, and power functions are intuitive in use. The square root and square functions are shortcuts for the power function with 0.1 and 2 power argument respectively. The log function is a natural logarithm, or the logarithm with the exponent in the base. The log10 function is a logarithm with 10 in the base. The sinus, cosines, and tangent are standard trigonometric functions. These functions receive the angle in radians as argument and return its sinus, cosines, and tangent values respectively as float values. In some cases, you may combine the functions and use round function with the other mathematical functions to receive the values with the accuracy you need. Finally, the pi function returns the value of pi. This function does not have any arguments. Now we will show you how you can run the considered mathematical functions on the SQL server. For that, you can use the select statement. As we move further, you will see that the mathematical functions can be used in a number of ways. Variables. Variable is a value that can change. The concept of variable is key in computer programming. The SQL server has system variables that we cannot control, but also an option for creating new variables. The variable should be declared and set. For that, SQL has two commands, namely declare and set. In SQL, the variables have to have an @ sign prefix. The system variables, the variables that cannot be changed, have two @ signs. When we declare the variable, we specify the data type. Variables can be numeric or character. This is what is called scalar variable, and variables can be tables. We will show the example later on. The scalar variables can be used for any algebraic operation. Also, SQL has so-called compound operators. Compound operator modifies the original value and sets the original value to the result. The compound operator can add a certain amount to the value, subtract, multiply, or divide by a certain amount. We show here the most used compound operators. In this example, we declare an integer variable and set its value to 10. We can view the content of the variable with the select statement. Now, with the compound operator, we add 5 to the myInteger variable. The new variable value is 15. If we will apply the compound operator again and subtract 5 from the variable, we will get the initial value of 10. The compound operators are very handy when you need to increase or decrease the numeric variable value. As we said before, the variables can be tables. We will declare a new variable as a table and simultaneously define its column names and data types. Here, we will populate the table variable with the imaginary kid age data. Then we will declare a scalar variable where we will store Emil's age. We will set the variable using a select statement with the filter. Setting variable values with select statements is a great advantage of SQL. This process will work with any other tables or views. The only restriction here is that if you are working with scalar variables, then the result of the select statement should be a single value. We can view the Emil age now, selecting from the Emil age variable. And of course, we can select data from the table variable in the same way we work with other tables and views. Conditional logic. There are situations when you can have several possible outcomes depending on the initial conditions. SQL has two forms for working with conditional statements, the if-else operator and the case operator. At first, we will explain how to work with if-else operator in SQL. Else operator is optional in the if-else pair. However, we recommend using it. The process for working with the if-else operator in SQL is similar to other programming languages. The if operator checks the condition statement. If the condition statement is true, the operator commands the SQL server to execute the SQL query followed by the condition. If the condition is false, the SQL server is instructed to execute the SQL query after the else keyword. If statements can only execute a single SQL query statement. You can overcome this limitation by using the begin-end block. The begin-end keywords signal the SQL server to treat the SQL statements inside the block as a single piece of code, a single block. We will illustrate the if-else statement with the begin-end block with the following example. At first, we declare a local variable in a bit data type. We will use this variable in our condition statement. The bit variable can only be 1 or 0. We set it to 1. Now we start constructing our if operator. With the following query block, we instruct one SQL server to execute two consecutive select queries if our variable is equal to 1. First query shows a message. Second query selects a filtered subset of data. Here it is a list of companies with a stock price greater than 100. With the else command, we instruct the SQL server to execute another block of SQL statements, namely show a message and list all companies from the table. The execution of the script results in a message and the list of companies according to the if condition. Let's change the value of our bit variable and set it to 0 and execute the whole script again. Now the SQL server walked through the else branch of the if-else operator. The result window shows a new message and a new set of data according to the queries in the else block. The other conditional logic operator is the case operator. SQL Server distinguishes two types of the case operator, the simple case and the searched case. The simple case operator evaluates an expression in its argument. The expression is an arbitrary user code that returns a single value. If this value is equal to the value 1 in the first when clause, then the SQL server executes the SQL query following then keyword and so on. If two when statements have the same value, then SQL server executes the query after the first valid when statement. If none of the values are found in the when statements, then the SQL server executes the query after the else keyword. The else branch in case operators is optional. Minimum number of when statements is 1. Maximum is 10. In the searched case, the SQL server values the conditions in the when statements. It does it one by one, the same as in the simple case. When the SQL server finds a condition that is true, then it executes the SQL query after the then keyword. If none of the conditions are valid, then the query after the else keyword is executed. An important note is that you cannot have begin-end blocks in the case operators, both simple and searched. The great thing about the searched case is that it allows to replace values in the results of a select query statement. We will illustrate this with an example. At first, we will construct and execute a query with the simple case. This case operator will calculate the length of a stock ticked for each record in the select query output. This length operator returns an integer value. If this integer value is equal to 1, then the ticker lengths column will receive a new entry 1 letter. If the ticker length is 2, then the ticker lengths column will receive an entry 2 letters, and so on. If the ticker length is more than 4 letters, then the new entry value is a string more than 4 letters. This was a simple case. Now let's construct a query with the searched case. The new select statement has a variable tier, which can be 1, 2, or 3. The value of tier for each company depends on its stock price value. If the company stock price is less than 30, then the tier value is 1. If the stock price is between 30 and 100, then the tier value is 2. Else, the tier is 3. Here we assume that the companies of tier 3 have stock prices greater than 100. Finally, we order the output results by the tier value. This is another way of splitting your data sets into buckets or tiers for your future data science work. Here you can explicitly control the boundaries of the subsets of data. Lastly, we will demonstrate how you can set variable values with the case operator. For that, we declare two variables, an integer and a string. The integer variable will be used in the condition expression of the case operator. Now we will set the string variable. For that, we will use the case operator. If the integer variable is equal to 1, then the string variable will be tier 1. If the integer variable is 2, then the string is tier 2. The same for the integer 3. If the integer variable is other than 1, 2, or 3, then the string variable is set to not defined. Now let's execute this piece of code. The select statement generates a result table with the string variable equal to tier 1. If we change the integer variable to other values, we will see that the string variable will change its values according to the branches of the case operator. Loops. Loops or cycles are repeating parts of code which are executed while a stopping condition is not fulfilled. In SQL, the loops can be created with the while command. The SQL statement after the while command is keep executed over and over again while the condition statement is true. To include more than one SQL statement in the loop, we can use the begin-end keywords to form a block of code. We will show how to construct the while loops with an example. At first, we declare an integer value that we will use as a loop counter and set it to 1. Next, we create a simple loop that prints the counter value to the message window and increments it by 1. Note that we are using a compound operator for incrementing the counter variable by 1. And since we have more than one SQL operator in the loop, we use the begin-end keywords to form the code block. Now we will demonstrate how we can do calculations with the loops. For that, we declare a decimal variable that we will use as an increment. We will change it from 0 to the value of pi. At each loop, we will evaluate a sinus function and break the loop as it will equal to the square root of the 2 divided by 2. When it happens, we convert the variable from radians to degrees and print it to the message window. Not surprisingly, the variable is equal to 45 degrees. Note that we used the round function to reduce possible decimals in the outcome value. Since we used the finite value 0.01 for the loop iterator variable, the inaccuracy in this method for computing values is inevitable. Custom functions. Sometimes you will need an SQL function that meets your specific needs. Custom function is a routine that accepts parameters, performs an action, and returns the results as a value. If you routinely use a certain piece of code in your work, it is a good idea to wrap it in a custom function. SQL Server allows you to create three types of functions: custom functions, stored procedures, and triggers. We will start with a create function command. With this command, we can create two types of functions, a scalar function and a table function. The scalar function returns a single value. Starting from SQL Server 2016, we can create a new function or alter an existing function with the same name with a single command. Alter keyword is optional. The custom function can accept one or more variable as a parameter. In the latter case, use a comma to separate the variables. The function will return a value of a data type specified after the returns keyword. To call the function, we can use select operator or just use the function name as it is a regular math function. We would like to note here that the custom functions can be nested. One function can call another, and the nested structure can be as deep as 32 levels. In this example, we will create a scalar custom function that calculates the length of a string. We will use begin end keywords to wrap declare and set operators in a single code block. After the function is created, we will use select operator to call it. The custom function is a database object, so we use a DBO prefix before the function name. Upon execution, the function returned the length of the string we specified as an input. Table custom function is similar to the scalar custom function. The only major difference is that it returns a table as an output. The SQL expression in the body of the table function has to be inside round brackets. We can retrieve data from the table custom function in the same way we work with tables using select operator. The simplest way to think of the table function is as a view with the parameter. In this example, we will create a table custom function that returns a list of companies from our table with the stock price above an arbitrary threshold. We will write a simple select statement with a filter in the body of the function. The filter has a threshold variable as a parameter. To call the function, we use a select statement where we retrieve all data from a table generated with the function under a certain value of the threshold. As we can see from the resulting table, we got the list of companies where the stock prices are above the threshold of 100. The other way to create custom functions in the SQL Server is to create stored procedures. The stored procedures may look like the regular functions that we considered earlier, but they are not. In contrast to the regular custom functions, the stored procedures can modify the database state. In other words, with the stored procedures, you can create, delete, and modify the database objects. However, unlike functions, the stored procedures do not have an input parameter and do not have to return a value. To execute the stored procedure, use the keyword execute or a short word exec. The stored procedure that we will show in this example will create a backup for the table company by sector. It will copy from the source table entries where the stock price is greater than the threshold. The threshold will be specified by the user upon the procedure execution. At first, the procedure will try to drop an existing backup table. If the table drop command will raise an error, the procedure try-catch block will catch the error and print the working message instead of stopping the execution. By the way, you can use try-catch structures in other SQL codes beyond the stored procedures. After the procedure is created, you can find it in the database among programmability database objects in the list of stored procedures. If the list is empty, then right-click on the list name and select Refresh from the menu. Now, we execute the procedure with the execute command. Since the backup table did not exist before we ran the procedure for the first time, the drop table command could not find it and resulted in an error. The stored procedure caught the error and printed the warning message. After that, the execution went smoothly and the table was copied. We can check that the backup table was created and it is not empty with the select statement. As we see from the result table, all stock prices are greater than 100. This is how the threshold parameter was set upon the stored procedure execution. Please note for the future that when a procedure is executed for the first time, it is compiled to determine an optimal access plan to retrieve the data. Subsequent executions of the procedure may reuse this plan and run faster. The third way for creating custom functions is to create triggers. In fact, a trigger is a special type of stored procedure. Triggers are automatically executed by the SQL server when a specified event occurs. The SQL Server distinguishes three types of triggers: data manipulation, triggers that can modify the data, data definition triggers that can create and delete database objects, and login triggers that react on the SQL Server login events. When we create a trigger, we have to specify its scope, a certain table, a database, or the whole server. The most commonly used triggers are those that react on table insert, update, or delete actions. Like other functions, triggers can be nested to a maximum of 32 levels. The trigger that we will create here will warn the user that a database table was dropped. This created trigger is idle unless it will detect a drop table event in the database. If so, then it will execute, or fire, as developers say, and print the warning message. We can find the list of triggers in the Database Triggers list in the Object Explorer. Let's see how the trigger works. We will drop a table with the drop table command. Right after the command was executed, we see the warning message in the message window. This is the message that we wrote when we created the trigger. For the future, you may create triggers that will block the drop table events with the rollback command instead of print, or execute a stored procedure for creating a backup copy. Connecting data analytics software. Exporting data. At some point, you might need to export your data into a flat file and then use it with your data analytics software. For small data sets, this approach is reasonable. There are two easy ways for exporting data into a flat file. The first is to use an import and export data wizard, which comes with the SQL Server distributive. You can find the wizard shortcut under the Microsoft SQL Server folder in your Windows program list. Choose the version that is appropriate to your systems, 32 or 64 bits. Once the wizard is open, click the Next button. And choose your data source. For the SQL Server, you can choose the SQL Server native client. Version 11 will work. Then click on the Server Name drop-down menu and select your SQL Server instance. For the server authentication, use the same method you used to connect the Server Management Studio. If you were using your Windows authentication, then leave the authentication setting as it is. Now, click on the Database drop-down menu and select your database name. If you do not see your database in the list, then click Refresh button to the right. On the next screen, select the flat file as your destination. Then enter the file name where you want to save your table data. In our example, we will save the data in a comma-separated value file named table. We recommend using the locale and code page settings the same as you have in your database. If you want the wizard to convert the data into a different code page, you can change the code page options. We can also change the file format settings here. We will leave the default format, which is delimited columns without a text qualifier. We will also leave the checkbox marked. With that, the wizard will save the table column names in the first row of the file. Click Next. Now we can choose the table that we want to save in the flat file. Note that your data source can be either a table or a view. After the source is selected, we can set the row and column delimiters. The wizard suggests a selection of row delimiters. For the Windows operating system, we have to use both carrier return or CR and line feed or LF to make sure the table rows will be stored as separate lines. If you are going to use the file on Mac, then CR is enough. For Linux, your file will look good with only LF row delimiter. Comma is the natural column delimiter for the comma-separated value file. So we will leave the comma delimiter with the default value. We can preview the file content by clicking the Preview button. One more thing we can do at this step is to edit mappings. For example, we can change the column names in the destination file. Here we will rename column ticker to the stock ticker and click OK. On the next screen, the wizard gives us a choice either to start the data export process immediately or to save the export settings as a SQL Server Integration Services package. We want to run it immediately, and so we click Next. Finally, the wizard asks us to confirm that we want to finalize the export setting process. The export itself will start right after we click the Finish button. Upon successful completion, we will see a window with the list of all stages of the exporting process. If the process would fail, then with this report we could easily detect the stage where the failure occurred. Now let's locate the file with the exported data and open it with the notepad. The content of the file looks exactly as we expected. The columns are delimited with the commas, the first row has column titles, and the first column title is stock ticker, as we called it at the content mapping stage. Now, the second way for exporting data is way faster. However, it gives less control on the formatting of the exported data and is only good for relatively small sets of data. We are talking about simple copy-pasting of the reporting window in the SQL Server Management Studio. Firstly, using the select statement, we will retrieve all the table content into the reporting window. Then we just click with the left mouse button on the empty field next to the column names and select all the table content. After, we click with the right button on the same field and choose Copy with Headers from the context menu. Now we can paste the data into any text of Spreadsheet Editor. We will paste the data in the notepad. As we can see, the buffer content was pasted as a tab-delimited table. It is perfectly fine to save the file as it is now. However, if we want to convert it to the comma-separated value file, then we can do some more manipulations. Select the tabulated space between columns and copy it to the buffer by pressing the Ctrl-C key. Then open Edit menu, choose Replace, and paste the buffer content into the Find What field. Enter comma sign in the Replace With field and click Replace All. With that, the notepad will search for all tabulation signs in the file and replace it with commas. The result of these manipulations can be saved as a comma-separated value file. Alternatively, we could paste the copied content into Excel and get a spreadsheet with the SQL Server table. Connecting Excel with Graphical User Interface. Here we will show how to retrieve data from the database into Excel using Excel Graphical User Interface. We will use Excel 365, but the process is similar for all Excel versions. After the Excel is opened and we started a new blank worksheet, we can go to the Data menu. In the Data menu ribbon, we should click the Get Data icon, the first icon to the left. Then we select option From Database and choose From SQL Server Database. Excel will ask us to enter the SQL Server name and the database name. We will use the same name as we used for connecting the SQL Server Management Studio. The database name is the name of the database where our table is located. Since we use Windows credentials to log into the server, Excel will not ask further questions and show us the list of instances that it found in our database. The first instance in the list is our table of interest. We can select the table name and get the content preview to make sure that this is the table we want to import. Now all we need to do is to click Load. Excel will show that it is working on the loading data, and then output the table content. Note that in the default format, Excel shows the table with filters. We can continue working with the table content using filters or convert the table to the format most of us get used to. For that, we will select the whole spreadsheet, copy it to the buffer, and then paste it without formatting to the new spreadsheet. Connecting Excel with Visual Basic for applications. If you are doing a lot of analytics in Excel or developing an application, then most likely you will need to know how to connect SQL Server with Visual Basic for application or VBA. At first, you will need to activate the Developer menu, which is not active by default. For that, go to the File menu and click Options at the bottom of the left column. In the Options window, find Customize Ribbon option, check the box next to the Developer menu item, and click the OK button. Now you have the Developer menu activated. Go to the Developer menu and find View Code icon. Click it to open the VBA editor. The other way to open the editor is to press the Alt plus F11 key. In the editor window, the first thing you need to do is to go to the Tools menu and click References. In the Reference window, you need to make sure that two references are enabled: Microsoft ActiveX Data Objects Library and Microsoft ActiveX Data Object Extension for data definition, language, and security. In this example, we will use version 2.8 for both references. Now we will create a subroutine for connecting with our SQL Server. We will need two set objects, connection and record set. The connection object will help us to set the connection with the server. The record set object will help us to retrieve data from the server. With the connection object, we will open a new connection with the server. For that, we need to pass the connection string to the object. Connection strings are nothing more than a list of parameters, a dictionary if you will, where we set values to certain variables. The list of variables depends on the driver that you want to use to connect with the server or the data provider. Here we will use the so-called SQL OLE DB data provider and instruct it to connect to our server LB Lenovo with Windows authorization and open SMP 500 database. If you will use other database servers like Oracle or IBM or other drivers, the connection strings will be slightly different. Also, you might like to add more parameters like connection timeout and other. For most SQL Server connections, this connection string will work just fine. For the record set object, we will write the query that we want to execute and pass the connection object as a parameter. Lastly, we instruct our subroutine to output all data that we will retrieve from the server into our record set object to the very beginning of the active worksheet, the cell A1. Now we can close the editor and create new control element to run the VBA script. We go back to the Developer menu and find the Insert icon. We want to insert a new button, which is the first item in the list of the form controls. After the button is placed, Excel suggests to assign a macro that this button will execute. We select our subroutine as the macro for the button. Finally, we give the button a user-friendly name and click on it. Under the hood, Excel runs the VBA code, connects with the SQL server, runs the select query, retrieves the data from the database table, and outputs the results into the worksheet. Now you know how to connect the SQL server to Excel with the Visual Basic macro. You can use this knowledge for building custom applications for advanced data analysis in Excel. Connecting IBM SPSS statistics. IBM SPSS is one of the most used data analytics software packages. We will show how to import data from the database table into IBM SPSS Statistics version 20. The process is common for other versions and even other software from the IBM SPSS family. After the IBM SPSS is opened, go to File menu, find Open Database menu, and click the item named New Query. With that, you will open the database wizard that will help to set up the data import process. Now click Add ODBC Data Source button. The Open Database Connectivity, or ODBC, is an industry standard interface for accessing databases. In the ODBC Administration menu, click the Add button on the User Data Source tab, and then select the SQL Server option as the new data source. In the following window, you will be prompted to give a name to your connection settings, provide an optional description, and the name of your SQL server. The next window is for entering your SQL Server login credentials. Since we are using Windows authentication, we do not need to change anything here. The following window will allow you to choose the database that you want to use. And finally, you can change the default language of your database and log file paths. It's okay to leave the setting as it is and click Finish. Now you can test your connection by clicking Test Data Source button. This step is optional, but it is always good to make sure everything was made in the right way. Now you have your data source set, and it is time to use it for importing the data. Click the Next button in the database wizard. The wizard will prompt you to select the data. At this step, you can select individual columns. For that, you need to expand the list with the table name, select the column name, and click on the arrow. You can remove the column by clicking the backward arrow. If you want to import all columns, you can just select the table name, click the arrow, and all columns from that table will be selected. Optionally, you can filter the data you want to import. For that, the wizard has a window where you can construct a filter for selected columns. To give an example, we will construct an expression that filters stock prices. With this filter, only the rows with the stock prices greater than 100 will be imported. At the last step, you can instruct the wizard to convert selected variables to numeric and set the default width for the string variables, or find the minimum suitable width automatically. We will leave all settings as they are and click Next. The wizard will show the SQL select statement that it will use to retrace the data from the table. You may notice that the wizard constructed the Where clause to reflect the filter that we created in the previous steps. Click Finish to launch the data import process. After the data is imported, you can examine the imported variables in the Variable View tab. To view the data, go to the Data view. All data is imported as expected. The data set contains only the records with the stock price greater than 100. One more thing we want to show here is the IBM SPSS Output Viewer window. This window shows the script that IBM SPSS software created with the help of the database wizard. Note that one field has a part of a database connection string. These string variables were used by the IBM SPSS to connect to our SQL server. The great thing is that the wizard helped us to create this string automatically. Now you know how to connect SQL Server Database to your IBM SPSS software. Connecting R. In this section, we will show how to use SQL Server Database Table as the source of data in our R code. We will use Visual Studio 2017 for creating the code. The code that we will show does not depend on the framework in which it was created. In the Visual Studio, we will start a new project, the framework as a preset for an R project. So we only need to choose R project and click OK. Now we have an empty file open, ready to be filled with the code. The R version that we will use in this example is 3.51. We will need the Open Database Connectivity driver to connect with our SQL server. For that, we will use an R library named RODBC. To connect with the server, we will create a new connection instance with the help of ODBC driver connect function. We need to pass the connection string to this function as an argument. In the connection string, we indicate that we are going to use an SQL Server driver with Windows authentication. For that, we type in the name of the driver, name of the server, name of the database, and set the trusted connection variable to be true. Now we will instruct the R code to execute the select query on the server using the connection that we just created. The result of the query execution will be copied to the data frame. To ensure that we retrieve the data that we need, we place the print data frame command at the end of our code. This is it. Now we will execute the code to see the results. We can see in the output window that the content of the data frame is the same as we expected to see. So we successfully established the connection to our SQL server from the R code. Connecting Python. In this section, we will show how to connect SQL Server Database to Python. For the demonstration, we will use Visual Studio 2017 and Python version 3.6. In the Visual Studio, we will start a new project. From the list of presets, we will choose Python Application. We have to note here that the code that we will create is independent on the framework where it was made. At first, we will import a Python library for Open Database Connectivity named PyODBC. This is one of the most popular libraries for connecting with the database server. Unlike R language, Python does not have built-in data frames. In this example, we want to load data from the server into a data frame, so we will need a library named pandas to create the data frame. With the PyODBC function connect, we will create a new database connection. For that, we will pass the minimum required connection settings, name of the driver, name of the server, name of the database, and set the trusted connection parameter to yes, indicating that we will use Windows authentication to log into the server. Next, with pandas function read SQL query, we will instruct the Python code to create a data frame and fill it with the results of the SQL query executed through the created server connection. To ensure that the data frame will be filled with the data as we expect, we will add print data frame command to the end of the code. Now we are ready to execute the code. The code prints the results to the Python default output window and to the Visual Studio output window. We can see that the data frame is correctly filled with the table content and has the same column headers as the source table. That means the connection to the SQL server was successful. Congratulations! You completed the course and now know way more than others. Feel free to join our community at scanba.org and apply for the Scanba certificate. You deserve it!
Thank you, Scanba.
Thank you, Scanba.
Thank you, Scanba.